Hi, thanks a lot for the opportunity. So I'm Rohit. I represent Ashwin GmbH. I'm CTO there. And we did this project, Physical Unclonable Functions for Identification of Large Distributed Devices. We were part of OpenCall 3, and our project partners were from EU partner. It was Ashwin GmbH. We are a SME. We are situated in Stuttgart, Germany. And we focus on, we have different products for IoT security. And our second partner was from US East Carolina University. It's also a leading public research institution. And we were in contact with Department of Technology and System. And they have experience with IoT and cyber infrastructure. So in this project, what we did is Ashwin had developed a solution. So our focus is IoT devices and how they are used in industrial environment. And we see now that more and more IoT devices are becoming part of industrial environment. They are becoming part of a critical infrastructure. And their security is of prime importance. And here the idea with the solution was that these IoT devices, currently they use static identifiers, which are based on strings. And these identifiers they are not unique, first thing, and they are just based on string. In this project, Ashwin worked on proof concept, physical unclonable functions. And what it means is that during the IC fabrication and manufacturing process, some kind of noise and some kind of variation occur in each chip. And in the proof concept, these variation can be utilized to generate some kind of unique identification and unique keys for communication which can be used. And there are multiple ways this proof concepts work. There are multiple techniques. And one of the techniques that we used was based on SRAM. And in SRAM, so here you see a conventional 6T SRAM cell, which has 6 transistors. And because how these transistors are produced and fabricated, there are some changes or unique changes at submicron level. And because of these changes, when this SRAM is powered on, then each cell of a SRAM has a random but a unique 0 and 1 bit. So in SRAM-based proof concept, what we do is we collect these 0, 1 bits for each SRAM of a device. And with those values, 0, 1 values, we generate a unique ID. And then later on, this unique ID can be used to generate multiple keys, which can be used for securing the communication. This was the solution. And so for us, the problem was that we wanted to test this for the scalability, we wanted to test for the performance, and it was not possible with multiple physical devices. There is a limitation how many IoT devices you can put out in the market or put it in your test lab. So what we did is we use these 2 test beds, one from EU, one from US. From Europe, we use virtual wall testbed, and from US, bridges testbeds from NSF. Virtual wall is from Fed for Fire. And there, the idea was that we would use these both testbeds. We would deploy physical nodes on these testbeds, and these physical nodes would be then orchestrated as a Kubernetes cluster. And on this Kubernetes cluster, then we will deploy some container application, and these container application will have different threads inside, and each thread in the container would emulate as an IoT device. So we simulate this whole proof process in the container environment, and then we make the calls for authorization, for bootstrapping of these devices, for authentication of these devices, and securing the communication channel with Ashwin platform. And in the experiment setup, there were 3 main components. One was the testbed, virtual wall, and bridges testbed. And then there was the Ashwin solution for generating the POF, for authenticating and bootstrapping the devices. And the third was this IoT fleet that we simulated using container application. So experimental execution, it worked as first we had to set up our development environment where we install all the tools which are required to connect to the testbed, to register and to reserve some resources on these virtual walls. And once we had that, then we emulated a Docker container as an IoT device. We created a Kubernetes cluster on the testbed. And on that Kubernetes cluster, then we deployed our container application. And from there on, we were able to scale our experiment, which means we were able to change how many containers we ran, which would transform to or translate to how many IoT devices we have on the Kubernetes cluster. And finally, we collected the data in a time series format, and we use Grafana dashboard to visualize this data with different interactive panels, and we were able to generate some insights about our solution, about our platform that we were using. In terms of project results, the metrics that we were focusing on first was to find the weak links in the POF process, weak link in the bootstrapping process that was happening on the cloud side. Second was to improve this whole process, both improve the performance, and then the third part was optimization. Here, with optimization, I mean for our solution, we were using blockchain technology also for securely bootstrapping these devices, securely store the metadata of these devices in the blockchain, and then we were able to record all the events which were happening in the life cycle of that device during the bootstrapping process. And finally, about the scalability test. If we wanted to test that if our solution and our cloud solution that we have is able to accommodate or able to handle millions of requests from these devices. In terms of professional performance, here I have two graphs from blockchain. Here I'm showing the response time. On the left side, there are containers where we are emulating 100 devices. On the right side, it's 100,000 devices, and we compare the performance. So the experiment, how we ran was an iterative experiment. Where we ran the experiment, we checked quickly how the data looks like, and we made some changes on the cloud side, on the device side, and then we compared this data with iterative experiments, and these are the final results. That in this graph we are showing the blockchain response time, and similarly there were other technical components involved on the cloud side and on the device side. We measured the response time of these servers for all the servers. So here it's just an example of blockchain server. In terms of optimization, for the blockchain solution, we use Hyperledger Besu, and it uses this IBFT consensus algorithm. And so this is an example of a Genesis file which is required to start a validation node and a regular node on blockchain network. And these are some of the important parameters which determine the performance of a blockchain network. So we were playing in this iterative fashion. We were playing with these parameters and try to check if we are able to increase the performance of this, if we are able to optimize the blockchain network for this particular solution. And finally, it's about the scalability. So here again, it's the success request from the blockchain server. On the left side, it's 400, and then on the other side, on the right side, it's 100,000 devices. So what we did is in each container application, we had 10 threads running. So these 10 threads would act as 10 devices. And then so this was one pod in terms of Kubernetes terminology, it's called one pod. And in this, then in one pod, we had 10 devices, and we were able to then scale these number of pods on the Kubernetes cluster. And in the end, then we were able to simulate 100,000 IoT devices and able to check how the performance of the servers are. So there were two parameters that we checked for the performance and optimization. One was about the response time from these servers, and the second was how many requests are received and how many requests were received successfully or gave the response successfully, how many requests failed to get the response from the server. In terms of project execution, it went quite well from our side as well, and from your side. And I want to thank Walton Institute, Trust IT Services, and Fed4Fire that we were able to execute this project on time. It was an amazing thing. So, and here I have put the list of further context. Mikko Ross is from Ashwin GmbH, and Cyprian, he was our contact point at ECU. And also some further links about our project and the blogs or dissemination articles that we have written about this process. Yeah, that's all from my side. Thanks. Yeah.
Jim. Yes, thank you very much for your excellent presentation and project. You know, it clearly ticked many of the topic areas for NGI with, you know, including security, blockchain, IoT, you know, large amounts of data, and so on. So it was very good. I guess just a similar question to the earlier ones. Did your U.S. partner give any insights into, you know, how they managed with the U.S. funding side that we can bring back to the NSF to let them know?
I think they didn't get any funding from NSF as far as I know, but I could check again on this.
Okay. Yeah, I think in our discussions in the review meetings, it was the NSF Bridges project,
right,
that was covering their side, but I just wasn't sure whether that was included in, or whether they had put in for the DCL on top of that, or whether it was just part of that. But that's fine. So
yeah, ECB, as far as I know, they are the leading coordinator for the US Bridges testbed. So yeah. I think from there they are managing their funding.
Yes, and then in terms of the Fed4Fire connections, how did you find that? Was it easy to do, or had you previous experience with Fed4Fire Plus, or?
Yeah, we had previous experience with Fed4Fire. Previously also we used a virtual wall testbed, and we had really good contact with Brecht and Peter from Kent University, and it was really easy to reserve resource there. There were two testbeds, virtual wall 1 and virtual wall 2. And we were able to, so for our experiment, we were able to reserve around 90 to 100 physical nodes on these virtual walls. And it was quite easy also to do this reserving process, commissioning these physical nodes, and to create this Kubernetes cluster on these nodes was quite easy. They have a really good documentation, and they have defined everything, the tools, the development setup that you need, and how to scale the experiment, how to collect the data, how to analyze the data with Grafana, and with this JFED tool that they have for commissioning the resources, reserving the resources on the virtual wall. It was really good.
Okay, thank you. Jorge, do you want to ask any questions?
No, you covered already the things I was planning to ask. So thank you very much. Very interesting presentation and very interesting work. So.
Thanks. Yeah, just one quick point regarding the US Bridges testbed. So during our project, there was disruption because of because of COVID-19. And they had a delay in deploying the US Bridges testbed, and I need to follow again with them. What is the process? What is the current status of the US Bridges testbed? And I think in future projects, at least they would, or other partners would be able to use this US Bridges testbed. And it's quite amazing vision that they have with the US Bridges testbed. Yeah, thanks.
Okay, thank you very much.